What that means is it is the scalar, or it is the gradient of some scalar function. Just like G, gravity, is the gradient of something. We call that the gravitational potential. Now remember gravitational potential energy? You guys remember back in physics 1 when you were, I don't know, maybe you did the roller coaster problem and you wanted to find the energy at all the different places. So you had potential energy and kinetic energy. And we had mechanical energy, which was those two added together. You guys remember this, right? And you remember potential energy is mgh, near the surface of the Earth. That's an example of a scalar field. The gravitational force is the gradient of that guy. And you also remember from physics 1 that when you're talking about gravitational potential energy, you're allowed to call anywhere you want 0. You guys remember that? I'm allowed to say I'm going to call down here 0, or I could call right here 0. The reason for that is because this scalar field is only defined up to an additive constant. Then when you take the gradient, that constant disappears. So I could, for example, say right here on the board is 0 potential energy. Then what I would always measure in any application is a change in potential. So if I went from here to here, that change in potential would be mg times my change in height. So this was 0. Here I had, I don't know, what is that? 1/3 of a meter of height, of energy. So mg times 1/3. Or I could, without changing anything, say the ground is 0. That's 0 way down there. That's 0 potential energy. So this would be, I'm almost a meter. This would be mg1 in energy. So the change in potential energy from here to here is still the same. It's still, I've gone from 1 1/3 down to 1. I still lost 1/3 of a meter in height. Everything is the same concept when we talk about electric fields and electric potential. So first off, the electric field, we're going to put in this negative sign for convenience, is the negative gradient of some scalar function that we're going to call V, where V is the electric potential. That's a scalar field that's only defined up to an additive constant. We can call V equals 0 anywhere we want. Anywhere we want, we can say V equals 0. V is electric potential. It's measured in volts. And 1 volt is 1 Newton per Coulomb. Let me think about my units here. V equals ED times meters. 1 Newton meter per Coulomb. Yeah, that's right. So you guys have heard of volts before. Your electric outlet on the wall that your computer's plugged into right now, we say is 120 volts, right? What that means is it's the potential difference from one side to the other is 120 volts. So if I've got some outlet and I say this is 120 volts, it might be that this side is 1,000,000 and 120 volts, and this side is 1,000,000. Because we always measure changes in potential. It's not that one side is 0 and the other is 120. Sure, why not? That's allowed. There's no such thing as defining the potential at a certain spot. It's always in reference to wherever you've called 0. And we will always measure changes in potential. Now, there's this philosophical argument that physicists have been having for the last 200 or 300 years over which one of these is a physical quantity and which one of these is just a mathematical construct that we invent to help us do problems. And some will argue V is the real thing. Every point in space has some electric potential, and we created this object called the electric field that measures changes in potential, measures the gradient of that. Other people will argue, no, E is the real thing, and V is the mathematical construct that we use just to make the math easier in some applications. Philosophically, it doesn't matter. You could take one stance or the other. I take the second one because V is not well defined. It's only defined up to an additive constant. E is 100% defined. Okay, so E is the negative gradient of the potential. That means it points downhill. If I have some scalar field, say this were my potential scalar field, the gradient we said a minute ago always points uphill. For convenience, we throw in an extra negative because forces point from higher to lower. So E is the negative gradient. The negative gradient of that guy would look like this and would point downhill. So here is some potential function. These are what the contour lines would look like. These would be levels of constant potential. And again, we can call anywhere we want 0. So if I said this level right here is 0, then this might be 10 volts, 20 volts, 30 volts, 40 volts. I'm getting higher in voltage. So look at the potential, it's getting higher. And now I'm getting, if this were 0, this would be negative 10, negative 20, negative, and so forth. I can call anywhere I want 0, just like I could grab this graph and say plus 100. Now we can't see it, but I just moved the whole thing up 100. If I take the gradient of that, this doesn't change. Take that off. So these are contour lines. Each one of these curves here would be what we call an equal potential curve. The electric field points perpendicular to equal potential curves and points downhill. So E is perpendicular curves and points from high to low. Points downhill. So if I had, I don't know, maybe an equal potential curves that look like this, maybe this is 20 volts, 15 volts, 5 volts. At every point along these curves, my E vectors would be pointing perpendicular to the curve and point from higher to lower potential. And so forth. Okay, now why do we care about this? Why do we care about electric fields and potential? What we want to find is energy and work. Remember, work is just the integral over force. So we want to think in terms of this diagram. So E is the negative gradient of V. I guess that's if I'm going this way. So if I have some scalar potential V, I take his gradient, throw in a negative for convenience, that gives me E. If I want to go backwards, if I wanted to go this way, I would integrate. So E here, V, would be the integral from point A to B, and there's a negative in there, E dot ds. So a change in potential is just an integral, a line integral of E dot ds. Now we know that to get from E to F, that's the electric field, that's newtons per coulomb. We just multiply by Q and get F equals QE. That allows us to define this guy, the energy, the electric potential energy, the same way, U equals QV. So V is the energy per unit charge, and I get the same equations here, negative gradient of U, or change in U is the negative integral from point A to B of F dot ds. So if I have two charges and I want to move them around, I want to find how much work is required for me or for the electric field, inversely, to move charges through space. I've got a few different ways I can get there. I can calculate the electric field, or I could even start here. I could say each of these charges creates a potential. From that, take the gradient and calculate the electric field, multiply by Q to get my electric force field, integrate, do a line integral through that vector field and calculate the work. That sounds like a lot of stuff. Or I could just take V times Q and be done. So this is the relationship between our four quantities we'll be working with. So I'm going to write down explicitly what each one is and what the units of each one is. E is electric field. This is in newtons per coulomb. F is the electric force field. This is in newtons. So this is how much force is being applied from one charge on the other. This, you only need one charge. You have a single charge in space, it creates an electric field everywhere. You put a second charge in that electric field, that second charge feels a force because of the field that was already there. That is F equals Q, your new charge times the electric field. We have V, that's our voltage. This is in volts, or V. Now, this is going to confuse you a little bit for the next few weeks. This is the only place I can think of in all of mathematics or all of physics where this happens. Our variable is V. So you'll have a question that says solve for V. Your units of that thing you're solving for has the same symbol. So we'll have problems where we'll solve and we'll say V equals 10V. And that can be a little confusing at first. This is saying the voltage difference between two places is 10 volts. That one's the unit. That's the variable you're solving. And then we have U. Same relationship is Q times V. This is the work or energy. And like all energies, this is in joules. Okay, so I've said several times, when it comes to V, we can call anywhere we want 0. If you got an electric outlet that your computer's plugged into, you could call one side 7 volts and the other one 127, because the difference is 120. In most applications, we usually, not always, usually call V equals 0 volts at infinity, because we're free to choose wherever we want. If we choose that, if we take this as our assumption for the moment, then if I have an electric charge sitting in space and I want to find the potential difference in relation to this, some distance r away. So I want to know the voltage right there, some distance r. Then my voltage will be KQ over R. This is, again, in relation to infinity. So a change in V, say I move from this position, say R2 to R1, I want to know what's the difference in voltages from here to here. My V2 minus V1 would be KQ over R2 minus KQ over R1. Okay, any questions so far? Okay, let's talk a little bit about energy. This is all just set up. We're going to be playing with V's and U's and E's and F's for the next few weeks. I'm just giving you background right now. Like you notice, I haven't really done any problems yet. I will set up this problem. So let's find the energy required or the work required to move a charge Q from infinity to some distance R from some fixed charge at the origin. Okay, so I've got here some Q1 sitting at the origin. I want to figure out how much work I would have to do to take another charge all the way from infinity and bring it in this close, some distance R away. So that's the calculation I'm going to do. Okay, now always keep this in mind. If a question says the work from you, that's the opposite of the work done by the field. Those two things mean the opposite thing. So work U is the opposite of the work the field does. This is just conservation of energy. If I'm doing work and it's costing me energy, then I'm putting extra energy into the electric field. It's bound up. It's bound up electrical potential energy. Just like right here, if I were to lift this thing up, I'm doing work to do this. Where did that energy go? I increased the potential energy. I increased the gravitational potential energy. Because now when I let it go, it falls. Okay, so I'm going to do the calculation from my point of view. How much work am I doing that's the opposite of the electric potential energy of the system? So I've got this charge here. Let's say it's some distance x away. I'm going to bring it in. Well, if they're both positive charges, I'm pushing that way. So my displacement is that way. I'm pushing that way because the electric field is pushing against me. I don't get to just move this guy for free. I'm fighting against the electric field. So my force is that way. Remember, work is the integral of force times distance from A to B. So I am pushing in the same direction that I'm moving. So this dot product is in the same direction. And my work will be the integral from infinity all the way out here down to some distance r of the force. How much force is between these two guys? KQ over distance squared dx. So that's just Coulomb's law there. So let's do this integral. The antiderivative, the k and the q come out. Oh, I need both q's, q1, q2. Okay, q1, q2. Antiderivative 1 over x squared is negative 1 over x, evaluated from r to infinity. At infinity, 1 over x is 0. So technically, we should write this as the limit as b goes to infinity, blah, blah, blah. We can hand wave infinite integrals nowadays. So I get 0 minus a negative, stick in r. That's k q1, q2 over r. So let me rewrite that. I've got this charge here, q2, that I have brought in from infinity all the way to this close to this charge that was already glued down. This guy is not moving. The work that I did is negative, or is positive, this one's positive, k q1, q2 over r. We define, I just said, we define the electric potential energy as the opposite of that. So the energy of this system, U, would be negative. No. I said I got to correct myself here. The work the electric field did was the opposite of that. We define, I always want to get this negative backwards, define electric potential energy as change in U is the opposite of the work from the field or equal to the work I did. So the change in electric potential energy of this system will be K Q1, Q2 over R. So now we take that, we don't have to ever write that down again. We don't ever have to do that integral. This is now our definition. The electric potential energy of this system is that much energy. That's literally how much energy is now bound up in the electric field. You bring two charges together, it's like you've compressed a spring. Think of the electric field as space is springy, and if you're squishing charges together, you're compressing a spring. The analogy isn't perfect, but it's decent. And now the energy is bound up in space itself. Space has been compressed. And if I were to let go, these guys would want to fly apart. How much energy would they have? If that all got converted into kinetic energy, that's how much energy we would have total. So that's what this is. But wait a minute, that looks a lot like that thing we talked about a minute ago, V. Another way to do this same problem, the exact same problem, is to say you've got one single charge in your universe that changes all of space. My potential difference in relation to infinity right there at that spot is KQ1 over R. Then U is just Q times V. Oh, well, I put a second charge there now. So the energy will be, just take that times KQ, Q2.